C'est bon.
Okay, great. So let me share my screen again. Voila. We are back. So a few things before we really start and before we really plunge into the conference and all the talks. Okay, so we can progress, everything fine. There will be okay, I have really trouble to share my screen, sorry guys. Now it doesn't want me to go through the slides, but I do it like that. So this is the program at a glance, as you can see. So the duration of this workshop is 3 days, from today until Friday, end of the afternoon, European time or GTM+2. In total, so we have more than 70 attendees, which is really, really great. That's a very great number for such a workshop. And as you know, we wanted the workshop to be quite small, so we can really form a group and share many things, and we can have more, I think, fruitful talks. Someone from ESA, and we will have 6 invited lecturers, 6 from company, and you can see the name of the company on the screen. In addition to that, we decided to organize 2 roundtables. One will be tomorrow at the end of the afternoon. This will be the last session. And another one on Friday afternoon, also end of the afternoon, just before the closure. The first roundtable will be chaired by Francesco Tacogna from the CNR in Paris, and it's really more science-oriented. And the second one will be chaired by Alberto Rossi from the CNES in France, and it's more technology-oriented. We will come back and discuss this again, but during the roundtable, so we will have a panel of, let's say, expert between brackets, but of course, everybody will be allowed to join, to share his viewpoint, and to just to talk and give his feeling, of course. So this will be really open to the entire audience, okay, for this roundtable. So some useful information now before we really start. So all talks will be recorded. They will be, after the conference, accessible on YouTube using a private channel, but we will send you an email at the end of the conference to have your agreement, of course. And if you don't want your talk to be accessible, it will, of course, be removed before we launch the private channel. But you will all receive an email at the end of the conference. Currently, the abstract are accessible, but only for attendees, only for people who register. We would like the abstract to be available to the So just a reminder for standard talks, the duration is 15 minutes, and we will have 5 minutes question after one from everybody in the audience. And for invited lectures, the duration is 30 minutes plus 10-minute questions. I will be the chairman for this morning session, for the first session, and I will, of course, take care of that, and we'll give a sign to the lecturer, to the speaker before the time limits. I already talked about the roundtables. Something also important, so all the microphone will be off during the talk, so we'll not be able to talk. If you want to ask a question, there is a button, so you can raise your hand. You can also use the chat. I will follow the chat. And after the talks, I will give you the right for opening your microphone and for being able to ask the question. For people involved in the session, your microphone will be open because you have the right. So I just would like you to close the microphone, not to disturb the speaker, of course. And also, I already advised everybody to switch off the camera, but the speaker, of course, to be sure that the connection is good for everybody. So this is about it. So as I said, I will be the chairman for the morning session. So this morning we will have 2 invited lectures. The first lecture by Exotrail and the second one by the CNES. And afterwards, so after the break, we will have 4 interesting talks about cathode and vacuum arc thruster. Because we are still a bit ahead of schedule, but it's always good to be ahead of schedule at the beginning, because usually we are not at the end. Before we start the session and the talks, I would like to know if there is any question before we start. So if you have anything to say, you can raise your hand, you can write in the chat. If you want, I don't know, maybe I forgot to mention something important. I think not, but if you have anything to say, we can take 2 minutes, and then we will be able to start in about 2 minutes. So the invited lecture by Exotrail. I don't know, Laurent and Alberto, Marlene, if you have anything else to add.
No, that's fine. There is one question, sorry, by Antoine Minuzzi.
Oh, sorry.
Yeah, concerning the slide.
So sorry, Antoine. Yes, I mentioned that at the beginning. So the slide will not be available, but they could, of course. If everybody agrees, we will make the slide available along with the abstract. But all the sessions are recorded. And afterwards, so after the conference, we will create a YouTube channel and make all the talks available. In addition, of course, we will require agreement, so we will send an email to all the audience, to all the attendees afterwards, or all the presenters, sorry, to get the agreement. But we could, of course, that's very good. I mean, we could. Anything else? No. So I think it will be time to start this 5th edition of the Micropropulsion and CubeSat meeting. So that's really a pleasure for me to start with Exotrail. So we will have an invited lecture by Exotrail. The presenter is Paul Lacombe, who is one of the co-founder of the Exotrail company. So Paul, you will have 30 minutes. I will open your microphone, so you will be able to talk, and then we meet you after your talks and for a dedicated question session. So Paul, you can
perfect.
start.
Merci Stéphane. The lecture today is about the history of Exotrail and how we went from doing lab research to now a company of 50 people dedicated to mobility in space. And obviously I have one presentation that I will share. So I think you can see the slides behind me. So as I said, at Exotrail, we are providing mobility solutions, and it's quite important to understand the company. We are obviously manufacturing propulsion systems, and that is why we are here today. But we are doing other things, and I will explain that later in the talk. So rapidly, Exotrail, we are a startup company. We founded the company in 2017 with 4 co-founders. And now we have 2 offices, one in Massy, next to Paris, where we do electric propulsion with 35 people. And we have 1 office in Toulouse with 15 people where we develop software. And software dedicated to using propulsion on a satellite. So it's all linked to mobility. We are quite well financed with mainly private money, but also some institutional grants. And it's quite important for us to have this mix of private and institutional money, so that we are a commercial company, but still with a very deep tech DNA. And well, when you do electric propulsion, it takes time, and it's really a technology challenge every day to have a thruster firing in space. Today we have quite a lot of customers. The first one being Eutelsat, which is a customer for both our electric propulsion solution and also our software, but also a satellite space or Thales Alenia Space. And this morning we revealed that we have also a US customer, York Space System, to put a satellite around the moon. So we will have Exotrail thruster around Earth, but also around the moon in 2022. We also have agencies as partners, mainly CNES and ESA. So why are we developing mobility at Exotrail? There are 3 main objectives in developing mobility solutions. The first one is to improve deployments. So propulsion for small satellites is really a necessity to complement the launcher, because launchers for small satellites are not dedicated, so they don't bring you where your satellite needs to be, and thus you need propulsion, and you need to know how you go from where the launcher releases you to where you want to operate. And this leads to an increase of performance, because you can have exact geometries which are not accessible without propulsion. And finally, and something we also insist on, is that we can reduce space pollution by 2 main activities. The first one is to be able to provide collision avoidance capability, which was not possible with previous small satellite systems. And also we can actively deorbit satellites at the end of their design life, so that they don't stay for tens of years in low Earth orbit. And to really focus on why we are providing propulsion, and why we think propulsion is a necessity for small satellites, because with propulsion and with large rockets, you can have the best of the 2 worlds, meaning that you can have precise and cheap launches thanks to large rockets, but you can also have an orbit that can change, and this is necessary for the commercial space sector. So now we go further with the real topic of the talk, which is what is the history of Exotrail, and how we started a startup company in the electric propulsion field, and how you go from lab ideas, which is the core of the MPCS, to a company that manufactures and delivers thruster that go to space. So obviously, it all started from research. It is highly complex systems. Well, you all know that. And we had 2 tracks, mainly developed by the CNRS and Stefan's team, which enabled us to have a proof of concept of a small scale thruster, in mid-2016, when the co-founders of ExoTrail started to think about what can we do with this kind of technology. So the picture you see on the left is the, let's say, 5 watts, a small old thruster. The performance and the lifetime of this guy were not exceptional, but still it proved that you can design very small thrusters, which could be compatible with CubeSat. Then, thanks to this proof of concept, we got a large funding from SAT Paris-Saclay, which is a tech transfer office. So it's an institutional company, let's say, that gives money to lab. So we was not a company at the time to go from lab prototype to integrated industrial prototypes. And in 2 years, we went from having a very basic proof of concept to having an integrated prototype, thanks to iterative improvements and significant funding, so that we can demonstrate that this kind of technology that was working in a lab could also work for the industrial world. And then comes the company. So we founded ExoTrail in mid-2017, so that we can start to plan fundraising. So in our field, I think it's barely impossible to start a project to have a thruster in space without having private funds. And we took 1 year to get our seed fundraising of 3 million euros in mid-2018 with this integrated prototype on the table. And this seed fundraising enabled us to have our first product sold at the end of 2019, sorry. And at the same time, to develop thruster to do in one in-orbit demonstration. So in 1 year, from 2018 to 2019, we have done 2 things. The first one being to develop thrusters that could go to space and that can ignite in space and move a satellite. And this will be the second part of this talk. But also, we were able to develop a product that was appealing to the market. So we needed to have an approach which was not only purely technical and oriented toward science, but also toward the market. And in the end, if we started with a thruster of 5 watts of power, we ended up with a thruster of 50 watts that was adapted to very small satellites from 10 to 20 kilograms. And this first product was sold to AAC Clyde Space for a constellation of Eutelsat. So on the right of this slide, you can see 2 flight models. So the first one on the left is for in-orbit demonstration with nanoavionics. And you can see the thruster integrated within the satellite before its launch. And on the right of the same picture with the complete integration written under it, there is another prototype that we sent to Aerospace Lab, which is a Belgian company. And this thruster is also in space. So we have now 2 thrusters in space, and we are handing over thrusters to commercial customers. So this is AAC Clyde Space, but other companies also. So I will come back to all those steps to explain you how you go from this idea to a company that has commercial footprint that can sell things to paying customers. So people that want a reliable thruster and that want it to be fairly cheap, let's say. So as I said, it all started with lab research, and mainly in CNRS, also supported by FNES. And we had, at Exotrail, we ended up having 2 parallel tracks, one on a 100 class thruster, which was developed by Stéphane's laboratory, ICAR, and another which has been developed by the GEMAC laboratory in Versailles, which was a 10-watt class thruster. Those 2 thrusters were lab products, so they were proof of concept. It was only the thruster part of a propulsion system. It was not industrial at all, meaning that it could not survive the launch environment. There was not the electronics or the gas delivery system, so that it could be integrated with a satellite. And here it's where science team need entrepreneurs. If you only have scientists in one team, then it's very hard to transition from doing research and having the best thruster and the best diagnostics, let's say, to characterize it, to having a product that you can sell. And with the other co-founders of Exotrail, we really had this opportunity to be at the right time, at the right place, because there was, back in 2017, there was a very high traction for propulsion, because at that time there was none that has been demonstrated for satellites with a weight less than 100 kilograms. And there was a need to start a company to do tech transfer. And it's really something that that was possible thanks to the Sat Paris-Saclay, because without high investments, let's say at the start, where you can tackle all the technical problems at once, then it's very long and very complex to be positioned in a front runner place without this private and institutional money that is 1 order of magnitude higher than what's typically get by the purely academic world. And so from those 2 thrusters, and I said thanks to quite a massive public financing to laboratories, we went from lab prototypes to something that could fly, and which was an industrial prototype. So on the right, you have the pictures of the different version of the thruster we've made in 2 years. So there was 4 versions of this thruster. And you have a mock, well, it's not a mock-up, actually, it's the actual prototype of something that could fly, so that could survive the launch, that could do the gas delivery to the thruster, that could handle power. And in 2 years, we went from having this proof of concept to having something that was integrated and could run on a satellite. At the same time, there was this company creation, and we needed to find a team. So during this technology development phase, there were 6 of us, 2 engineers working in the lab that was financed by the Sat Paris-Saclay, and 4 co-founders of the company that were working half on the technology development and half on the developing the market traction and commercialization of the thruster, and preparing the fundraising to go from this prototype to an actual flight model to be embarked on a satellite. And also, it is required to have a permanent workforce that is 100% dedicated to developing this concept. Otherwise, you are you are too slow and you cannot cover all the different tracks required to have something in space. Because it's, well, the plasma parts may be the most complex parts here, but mastering the electronics, the fluidics, the environmental constraints during launch is also something which is totally critical to have a product that can be sold. And so the team at the time was, well, 4 + 2. I could not find another picture of us. And you will see how the team will grow to get to this first industrial milestone, let's say, where Exotrail raised private capital to really kickstart the development of the company, while still having strong public support. So from the industrial prototype that you saw on the previous slide to this one that were those two that can fly, there was massive work to be done. And so we went from a team of 6 to a team of 20 in 3 months. So that in 1 year, we can have something that can fly and that can be ignited in space, that can move a satellite in space. Obviously, this company growth was mainly on engineers and PhD. And also at that time, we partnered with Stefan's laboratory to still focus on research. So we have an agreement, common laboratory, that Exotrail is a company that develops products, but those products are rooted in science and in research, because we need to be at the forefront of these markets so that our products are appealing to our customers. And thanks to this rapid development, we had our first sales to AAC Flight Space on the propulsion subsystem and also on the software solution. I will come back to the software solution after, because it's not at the core of this talk here. And so now with the interns and all the people that we have, we were something like 22, 23 by the end of 2018. So the team was growing quite fast, and it was required by the pace we had to have so that we can deliver industrial products. And now we are at a phase where we have industrial products, meaning that we can, well, mass produce in the space sector, let's say. So thanks to a new round of investments, we are now capable of delivering between 20 to 50 thrusters per year in various configurations. Those configurations span from 50 watts, so the one we have flown for our in-orbit demonstration, to 800 watts of input power with a clusterization of several thrusters. And we have those two tracks that I talked about before. So we have a strong track to have an industrial product, and you can see on the right the different product that we can offer. They are all based on the same base building blocks, but they can be arranged in many different ways so that we can cover all the needs of our potential customers. But we also have a very strong product improvement line because we still need to improve the performance and to have products that are up to date. We also industrialized our software solution, and now we have a end-to-end solution with hardware and with software. So we deliver an integrated hardware solution, but also all the means that are necessary to use them, so that you can have a one-stop solution, let's say, for a customer that doesn't need to take care of anything into propulsion, and that can handle that with Exotrail's products. And this industrialization led to a new increase in the number of people that we have in the company, from 20 to 50 now. I don't have a photograph for this because with COVID restriction, we could not meet all together. But now it's not only engineers and PhD people that we have in company. We have a growing sales team. We have general and administration people, so HR people, offices administration, things like that. Obviously, we still have strong team in product development and operations, but also now in production. So we had a much higher variety of profile in the company required to sell propulsion system to many actors. So this concludes the history of Exotrail, and I presented how we went from being a very small team in a lab to now a company of 50 with industrial products selling to a large number of customers and commercial customers. And I will jump to a more standard company presentation to explain you how we present Exotrail and why it is very important to have a company structure and to have this structure to sell products. So the company is positioned, said, on the mobility sector, well, mobility solutions for small satellites. And we cover all the needs of satellite integrators and operators on this topic. We go from design to the deorbitation of satellites, thanks to our software solution that can do mission analysis, they can do optimization of trajectories, and that can also cover the operation of the satellite, both on the flight dynamics side, so propulsion side, but also on the operations on the commanding of the satellite itself. We obviously have our propulsion systems, so as I said, ranging from 50 watts to 800 watts, so that we can cover satellites from 10 kilograms to 250 kilograms. So the vast majority of satellites that will be launched in the coming years. And we will also offer, and I will come back to that at the end of the presentation, a service to provide mobility, but not as hardware that has to be integrated on a satellite, but as a service that can be purchased from the launcher to be positioned where your satellite needs to be, so that you can outsource, let's say, the propulsion capability of your satellites. So now I'll present our propulsion family of thrusters. Here I will present the product itself, and I will also present you our in-orbit demonstration results, which have been presented in a conference a few weeks ago, and which are something quite new in the field for all thrusters. So here is what a propulsion system is. So I think many of you work on the thruster side, what we call thruster head. It's where the plasma is created. So we have one version of a 50-60 class thruster. We have one version of more 100 to 150 watt class thruster head. We use all effect technology, which is quite known in the field, but we miniaturized it, and it is a real challenge. But to have this plasma generator working, you need other subsystem. As I said previously, you need obviously something that can provide that can store the gas first, so a tank, and that can provide gas to our anode and cathode. So we need a propellant management system. And you also need something that can provide the high voltage required by the thruster. And at ExoTrail, we are producing all of this in-house, and we have the complete understanding, and we master all those 4 bricks, because we think that it is a necessity for small satellite operators to have integrated propulsion systems. And here you only plug data and regular power to the thruster control units, and this propulsion system handles everything else to provide thrust to our satellites. And here is all the range of products that we can offer, from very tiny ExoMG Nano, as we call them, which can take roughly 1 unit of CubeSat plus 1 tuna can. So protrusion on the satellites, which is standard, all the way to a massive cluster of 4 thrusters that can go to 800 watts, and that can provide hundreds or even kilometer per second of delta V capacity to small satellites. And all of this is based on the same building blocks. So the thruster head is changing, but it has a lot of commonality between the 50 and the 150 watt class thrusters. But the electronics and the gas delivery system are the same, and are just multiplied, clustered, because we think that improving the redundancy here is critical to the safe operation of satellites and small satellites that cannot afford to have 2 big typical thrusters, which are more expensive and which are which may lead to a loss of redundancy. And maybe so. So now we have commercialized our ExoMG Nano to AAC Clyde Space, and with York Space System, it is a cluster of 2 that we are providing to go around the moon. And so this slide is not up to date with this morning announcements, but we provided our system, as I said, to quite a number of companies. The first one being Nanoavionics for our in-orbit demonstration. And it is quite interesting to note here that we delivered this thruster in September 2019, and we had the first firing in December 2020 after 1 year of storage in India without any conditioning of the thruster. So we have more than 1 year of shelf life. We also delivered the thruster to Aerospace Lab and now to Eutelsat. And we also have international customers as a Singaporean actor and now York Space System in the USA. And now we'll go deeper into what we have done in our in-orbit demonstration. So it is a ExoMG Nano thruster that has been embarked on a 6U CubeSat made by Nanoavionics. And you can see that we fired this thruster on the satellite in a vacuum chamber prior to go to space. So we validated that the spacecraft was working with the thruster on this platform. And you can see here the satellite being ejected by the launcher on the right, and also the maneuvers that we've performed. So we changed the orbit by around 10 kilometers over the course of 2 months. That was the date of the operation of the thruster for this in-orbit demonstration. So I will go quite quickly on our ExoOps software suite. It's not the main topic of the talk here, but there is a need of software solutions because of the rise of constellations. So you need to have autonomous solutions that can deal with maneuvering. because propulsion creates quite a lot of problems for operators because they need to take that into account in mission planning. It's much more complex to include propulsion than to only have the payload. And there is a need of cloud-based solutions, and that is why we developed Exorbs.
You've got 3 more minutes, Paul.
Yes. I will have to go much faster at the end. So this Exorb solution has been sold to various actors, mainly Eutelsat, Thales and Space, and institutional customers. And here is the interesting part of the talk on the Air2 mission. So it has been launched in November 2020 in a low Earth orbit, in low Earth orbit. And this is our thruster on the satellite here. Yes, and it has been launched in India on a low inclination orbit. So I already described that. It's a full complete subsystem where the platform is only providing us with data and power, and we have everything integrated in the propulsion subsystem. And as I said, you not only need the thruster parts, but you also need to control the mass flow, to store propellant, and to control and deliver power to the thruster. I think you all know how all thruster works. So you have a cathode that emits electrons, and those electrons are ionizing xenon gas, which is then ejected at high velocity. And we think that Hall effect technology is really necessary for small satellites because it is the one that provides the highest thrust to power ratio. And on small satellites, you are much more looking for power than looking for mass. So we think that the trade-off between power and ISP favors Hall effect technology. So we are, let's say, an industrial company, so we needed to see how the thruster was behaving in space. To do that, we performed passive checks, but also active checks. Passive checks were mainly monitoring the temperature, monitoring the power consumption, and monitoring the propellant management system. And you can see on the graph on the right that the temperature are totally within normal limits, and there was no major problems here. So going from +10 to -10 degrees, which is well within the limits of the design of the system. And here, well, you don't have the exact pressure, but the pressure that we got indicated that there was no leak during launch on the tanks. After that, we commissioned the thruster itself. So we performed active checks to start the thruster. First, we put mass flow to the anode and cathode. Then we powered the cathode heater and the anode. And we performed the first ignition at the first trial. So you all know how, well, that we have to put gas in a thruster. We had to heat cathodes. So we have cathode with heaters to improve reliability. And we polarized the anode at high voltage, and there was no indication of any problem here. And we did the first ignition attempt with a hot cathode, propellant flowing to the anode and cathode, and we polarized the anode. And you can see here that we had both voltage and current to the thruster for 10 minutes. And there was a significant change in the orbit that indicated that the thrust was created. Here, so I will finish by this, those 3 slides. We developed Exorbs operations so that the integrator doesn't have to handle all flight dynamics. And by saying flight dynamics, it's how you go from position A to position B, where you have to fire, and how you can retrieve the events that happened. So what is the thrust? What is the specific impulse of your system? And does everything went as planned? It
will be time to conclude, Paul.
Yes. So with Nanoavionics, we had GPS data, and this GPS data enabled us to track the satellite and to get the actual semi-major axis for here, and that we could correlate with the firings. And here you can see that actually something which is quite interesting and that could be discussed within this workshop is that the thrust that we measured in space was higher than the thrust we measured on the ground. We don't have clear explanation for that. We think that it is mainly due to facility effects, but we had an increase of performance of 20% from ground tests to the thrust measured in space, and we performed tens of firings, and on every firing it is the case. Here we put 5 of them, and it's something that is so we cross-check the real measurements made in space, and they all are in agreement with this unexpected behavior. And so to conclude, this in-orbit demonstration was a necessity for the company, both in terms of communication, but also technical aspect, because it enabled us to both prove that our propulsion system was working and working fine, and that all the algorithms that we developed for our software were working and were able to operate a satellite in space. I'll jump to the last slide. Thanks for your attention.
Thanks a lot, Paul. This was really an interesting talk. It's your story is really amazing, and probably we're going to hear about more story like that in the coming days. But that's really impressive what you have been able to achieve, all of you guys, in within only 5 years, I think. So congratulations to all of you. We have already 2 questions from the audience. So the first one is from Rodion Ayupov. So I will just, Rodion, I think your microphone should be open now. Or did I make something wrong? Rodion, can you hear me? No. Okay. So then we have another question from our colleague from South Korea, Wonho Koe. So Wonho, do you hear me, Wonho?
Yes, I can hear you.
Okay.
Can you hear me?
Yes, great to have you among us, Wonho. So you can ask a question to Paul.
Thank you very much for the very nice and interesting talk. My question is, you mentioned that you achieved 50 millinewton per kilowatt. And I'm wondering if this value is from the ground test or from the space.
So the 50 millinewton per kilowatt is something typical of all thrusters. Actually, so it was based on the ground test. So we should be slightly higher than that with in-orbit values. Yet on this specific graph, it was more generality on all thrusters, and why we think the technology is better suited for putting satellite in the right place in the right time. It was not the exact number of a millinewton per kilowatt. So just to give you an idea, on the last point at 3 millinewton in space, the power used by the thruster was 55 watts of input power.
Okay, we did a similar experiment at around 60 watts anode power, and then we achieved something like a 60 millinewton per kilowatt. And this value highly depends on the gas pressure when you do an experiment. And I'm wondering what was the gas pressure in your case when you operated the Hall thruster?
So when we are doing a test in our vacuum chamber, so, well, we have limited amount of money to put in that. So we have one vacuum chamber that can run at 7, 8, 10 to the minus 5 millibars. It's where we have our stress scale. And we are upgrading our facilities to go to 2 to 3, 10 to the minus 5 millibars in a very short future.
Okay, thank you very much.
So it's still high for precise performance testing. Yet, well, giving our resources, it's what we can do best.
Thank you again.
Maybe I can answer
there is another
question because it's on the discussion. So yes, I think that to have something to deorbit your satellite at the end of its life will be mandatory in the coming years. We have seen 3 main tracks. The first one being to go at low altitude, say, just like Starlink. They don't want to go high so that if one satellite fails, it can re-enter in 10 years or so. There is another track, which is to put propulsion on a satellite, but this one would require satellites to be highly reliable so that they don't fail when they are too high to the orbits. I think this is a possibility, but the agencies and the regulators will need to enforce design life and not to extend the design life of the spacecraft, which is not done now. And you also have some passive limitation for orbit lower than 1,000 kilometers, let's say, with drag sails or electrostatic tape. So there might be 3 kinds of answers, but I think that we will go to stay low when you are in low Earth orbit and have active propulsion, not extending the design life of the satellites.
Thanks a lot, Paul. Rodion, do you want to make any comment?
Actually, thank you very much for your presentation and answer. I think I get it, your position. It's quite interesting. And actually, I wanted to ask you mostly about collision avoidance requirements. What do you think? Considering all these mega constellations, they all will be deployed. Is it will be some motivation for ordinary satellites to implement propulsion just to avoid a lot of spacecraft in orbit? What do you think?
So collision avoidance is something that we tackle. So in our exorbs, there is a module to compute collision avoidance maneuvers. But so I do think there is a need for propulsion here. So not propulsion, which is very powerful, well, that provide a lot of thrust, but still it is required. And you have quite a lot of different initiatives. So both from private companies, such as Slingshot Aerospace, that want to aggregate all the positions of the satellite and the maneuver plan so that they can compute very accurately conjunctions. And you also have the US government that has quite a, which is pushing very hard so that operators give this same kind of information to GSPOC, which track satellites and provide collision avoidance, conjunction messages to the community so that they have the most up-to-date data. So there is both public pressure to have, let's say, an open world of position of satellites, but also some private initiatives. And I think it will be necessary to have propulsion to do collision avoidance.
Okay, thank you very much.
Thanks a lot, Paul. We have a last question from Christophe Coppel.
Yes, hello everybody. Thank you for your presentation. I was wondering if the increase of trust in flight may come from some erosion or sputtering of your anode. What do you think about that? And did you measure that erosion on ground test to see what happened on the anode?
Yes, so we are sure it's not from erosion because so we have 2 months of operations with some, so to perform the passive check, active check, and firing, it has to be done in 2 months. So we did not significantly eroded the ceramics during the its demonstration. So on the ground, there is erosion of our ceramics, but for the design life of the XOMG Nano, there is no. So it is an issue, but it's not the limiting factor of the lifetime of the thruster yet.
Okay, so thanks a lot, Paul. We still have more questions, but it's time now to conclude and move to the next invited lecture. Thanks a lot, Paul. It was really a great talk. I also have questions, but I will ask them to you directly. I saw that there are still questions from the audience in the question and answer. Maybe, Paul, you can just answer them directly using the chat or using the question and response on Teams. Thanks a lot, Paul, and congratulations for your talk.
Thanks, Stefan, and I yield the floor to Alberto.
Okay, so Alberto.
Yes, good morning.
Good morning, Alberto. So great to have you here among us. So Alberto is one of the organizers of this conference. So I will leave the floor to you, Alberto, for a talk from the French Space Agency about micropropulsion activities. It's up to you, Alberto. You've got 30 minutes.
Yes, thank you, Stefan. Thank you to everybody. Do you see my screen? It's okay?
No.
No?
I don't see it.
Okay.
It's okay.
And now it's okay for the presentation?
Okay, Alberto. Yes, it is.
Okay, thank you. Thank you to everybody to be here. I hope that next time we can meet each other in a physical place, but for the moment, it's the only way we have. So let's start. So I will present you today the CNES electric micropropulsion activities. So I prepared this presentation with my colleague Gaël GSN. I can start with my presentation. So I'm Alberto Rossi. I'm the head of the space propulsion of the propulsion pyrotechnics and the aerothermodynamics office at CNES, the French Space Agency. So I can start with a brief introduction of the role of the CNES. I can say some words about the CNES mission. And then I can tell you something about French micropropulsion environment and our activities. I selected some activities because I have only 30 minutes. So we have a lot of activities in the field of micropropulsion, electric micropropulsion. And I selected 8 activities today, and some words at the end, some conclusions. So the CNES is the French Space Agency. It was founded in 1961. It's a scientific and technical public establishment of industrial and also commercial nature, with the authority to manage its own budget. So we help French companies, for example, to develop its activities in the space fields. And we help also laboratory to develop its activity in the scientific way. So we provide also overall vision, a general vision of space solution. And we also build the French space politics. So some words also on the CNES organization. We have 4 major sites. In the biggest site in Toulouse with 1,700 people. So we have a site in Paris, Paris Duménil, where we work on the rockets and launchers. We have also our headquarters in Paris, the city center, and of course we have also our launch site in Guyana. That is also also the European launch site and European spaceport. We have a budget of 2.4 billion per year, and we have in the world the second world budget per inhabitants. So the CNES missions are divided in 5 major spheres of intervention today. The first sphere is Ariane program, with the possibility to give to Europe a space access. And then we have a scientific mission linked to the exploration and use of space technology, and the development of space instrument and all that is connected with the science in the space environment. Earth observation, so we work a lot of satellite platform for the Earth observation, telecommunication satellite, to give to France the possibility to have telecommunication satellite, efficient telecommunication capabilities, and also today, very important, a defense role with very high resolution optical observation, intelligence gathering, and and especially highly secure telecommunication and surveillance from space. This is the 5 major spheres of intervention, our 5 missions today at the French Space Agency. So if we switch on our subject, the French, in general, the French electric propulsion environment is very rich. Let me say that it's a unique case in the world, because in a little nation like France, we have a great panel of different electric propulsion technology, and we can cover today all the power range for a satellite platform. We have in the domain, in the class of the micropropulsion, we have also a lot of technology, a lot of different technology, because we have a lot of actors today with that develop different kind of technology at different power level. So it's a unique environment in the world, and we can work with all these actors to develop this at the same time, this different kind of technology. So I can continue with some selected activities with this actor, with our scientific laboratory in the domain of micropropulsion. So we divided our activities in 2 types. First type of activities regards the improvement of our test facilities. We want to give to our actors, to our laboratory, the best test facility and all the test capabilities today for new markets, for new business in the space domain, in the space industry. So, for example, we will start to work at the end of the year to a multi-axis trust balance. It is a new activity at CNES that we start at the end of 2021. This is an equipment we need for the qualification because of today the quality, for example, of the trust vector is only evaluated indirectly from a plasma probe in front of the thruster, for example, and we want to give a direct measure of the quality of the thrust vector with a real thrust balance. So multi-axis thrust balance is very complicated devices, but we want to make an effort to develop this kind of device and give it to the French micropropulsion community. We think about two main applications. So, as I said, a precise evaluation of the thrust vector direction, and also a possibility to test a thrust vectoring devices. We will speak about this late in the presentation. But today, if we have a thrust vectoring devices, we want to be able to qualify it and to evaluate its capabilities. And also in the same on the same topics regarding the test facility, we developed with Onera, our partner, a measure of the thrust with a measurement of the plasma pressure in the plume of the thruster. Because we can't use always a thrust balance, and thrust balance is also a complicated equipment, so we want to give a indirect measurement of the thruster, a good indirect measurement of the thruster. Because each thrust balance is very specific to each vacuum chamber, and with the thrust balance, for example, also we cannot do an in-orbit measurement. So we developed a thrust sensor that uses a high-quality sensitive quartz micro resonator as force sensor. Different activities on this subject show that the sensor is robust and sensitive enough today for the measurement of the plasma pressure and for the measurement of the thrust. So it's a very important activity for us to improve our thrust measurement with these two activities. Another activity that is also linked to our to the subject of test facility is the measurement of the radiated emission of the from the plasma from a electric thruster. We know that it's a very, very, very complicated topic, the electromagnetic compatibility of electric propulsion, especially radiated emission. Everybody knows today that it's complicated to measure this kind of emission from a thruster because of a thruster can only work in a vacuum chamber, and we also need an anechoic chamber. So to couple anechoic chamber and the vacuum chamber is very, very, very complicated. So today some test facilities exist in the world, but they are not perfect. So we'd like to give to the community a new method, and a new test facility to measure this kind of emission from an electric thruster. We divided this activity into 4 major axes. First of all, the modeling and simulation of the interaction between microwave antennas and the plume of the electric thruster. Today, it's very complicated to simulate, for example, a plasma discharge of Hall effect thruster, but it's more complicated to simulate the plume effect and the plume radiation of a thruster. But we are trying to simulate this environment, and we have a PhD in this moment, and we will there will be a presentation and with more details on this topic next days. Another axis is the measuring of radiated emission microelectric thruster. We have also an activity to measure without an anechoic chamber, with other techniques, the radiated emission. And we are also exploring other methods to easier build a test facility for measuring this kind of emission. And also we are thinking about an in-orbit measurement mission because of we know very well that in a very in-orbit measurement it's more representative that a measurement here on the ground. So the other important subject for us regarding micropropulsion is new technologies. We work, as I said, on the test facility improvement, and we also work on new technologies or on the improvement of actual technologies. So, and activities we have with the French National Scientific Research Center. Now it's the development and the study of a two-stage micro effect thruster with an inductive ionization stage. We are very proud of this thruster because for us, it's not real, of course, a new thruster technology that will be in space tomorrow, but it's a laboratory for this thruster that can allow us to better understand some plasma mechanism, some plasma physics equation, and it's a real laboratory thruster, very important for us. We learn a lot on the plasma physics with the thruster. There are some interesting publication on the subject, thanks to our colleagues of CNRS. So, as you know, in a two-stage effect thruster, we separate the ionization source and the acceleration region in the thruster with respect to a classical effect thruster. So we have some important results. When we work, when the thruster is in a two-stage mode, it's possible to operate this thruster at a lower voltage than the minimal voltage required for a single stage operation. We have the reduction of the discharge current without changing the total ion current, and especially the breaking mode oscillation that appear in a single stage in all effect thruster operation. Here with the two-stage operation tend to disappear. So it's a very, very important result for us. And also the plume divergence decreases in the two-stage mode. So we learn a lot, and we continue to learn a lot with this project, with this thruster. So we work also on the clusterization of Hall-effect thruster with Exotrail today. It's a project we have started last year with Exotrail. It's very important for us to demonstrate the capability of micro thruster, micro Hall-effect thruster in this case to work together in order to reach higher thrust and power for large satellite platform, for large satellite needs. Clustering is very important because we do not need to design and qualify a new, for example, a new bigger thruster with more power, more thrust, and especially for little actors today, it's very important. There is, with the thruster, there is also an intrinsic redundancy that increases the reliability of the system, and we can extend the performance range. So it's a very important capability today, the clusterization of a thruster. So we are concentrating on three main aspects: the interaction between multiple anodes and cathodes. So the interaction between two thrusters very, very close. The cluster's performance optimization, and the ignition strategy. So it's another very, very important activities that allows our actor to use this kind of technology instead of build, for example, another and qualify another thruster. So we have also another activity today with the Exotrail. It's the magnetic thrust vectoring for micro Hall-effect thruster. So as I said, when I spoke about a multi-axis thrust balance, today we want to develop the thrust vectoring capability for micro Hall-effect thruster, a magnetic thrust vectoring capability, because of it, it's not maybe not everybody thinks like us, but at NES we think that a mechanical device is too complicated for micro propulsion. So we think that a magnetic static device is easier to develop and to build. We know that it's not easy at all, but it's easier for, in our opinion, that a mechanical device. So we restart from a study, a CNRS and Safran study of 2009, when they demonstrated the possibility and to change the thrust direction in Hall-effect thruster using a device that changes the shapes of the magnetic field. Today we want to apply this to a micro Hall-effect thruster. It's more difficult, of course, because the thruster is smaller, it's a very small thruster, smaller than the example of 2009. But we have some first good result, and we want to continue on this way to try to develop this kind of device. There are some advantages of a magnetic thrust vectoring, of a static magnetic thrust vectoring. We think that we have a lower cost and a lower mass than a cluster of thruster, of course, because we can also vectorize the thruster in a cluster of thruster using more thrusters. But if we have only one thruster, it's better. We can have lower or similar total mass than the mobile steering device. A mobile steering device, a mechanical steering device, is very heavy and complicated. For little angles, it's a very performance device. And we can also change the thrust angle during thrust operation. So it's very important for the attitude control system of the platform. And we can do attitude control actively during operation, as I say. But
you've got 5 minutes left on it.
Yes, thank you. There are a lot of challenges of this in this activity. It's very complicated device. Also, if it's less complicated than a mechanical device, because of especially because of the erosion of the anomaly erosion of the walls of the thruster with the change in the magnetic length direction. So I want also to speak about an activity that we have with COMAT on the vacuum arc thruster. On the vacuum arc thruster propulsion. There will be a free presentation from COMAT, so I don't tell you a lot of details. We work with COMAT from 2 or 3 years on this technology. It's another very important activity because it's a completely different technology with respect to all effect thruster on the IONS engines. We support this activity with different projects, and we support also a demonstration mission that will be soon in space with COMAT. So I go fast here. And also another activity very important for us is the development of the cold gas propulsion. Because we developed in the past with Air Liquide a valve, a multifunctional valve dedicated for electric propulsion. But we saw that we can use this multifunctional valve as a cold gas thruster itself. So today we started this year to qualify this valve as a thruster itself. It's a very efficient cold gas thruster, and we hope that we can finish very soon this qualification activity and give to the community this kind of thruster. So some words for the conclusion. As I said previously, we had 3 main targets in the field of electric micropropulsion: the improvement on test facility, to reduce qualification cost and time, and developing new technologies. Today we know that one of the most difficult activity is the qualification and test of the thruster in the ground, and we want to improve our capability and our capability to test the thruster on the ground. We have a large number of different propulsion technology. In French today, it's very positive, but we have to improve each of these technology. And there is also a strong international competition, so we have to help our community to maintain a good level from a technological point of view and from a scientific point of view. Thank you very much.
Many thanks, Alberto, for this very interesting talk from the French Space Agency. So we already have a question from Christophe Coppel in the audience. So I will Christophe to.
Hello.
Hello.
Alberto, thank you for your presentation. I was wondering about trust vectoring you present, please do not forget that there is a need for spacecraft of having 3 degrees of freedom. With such trust vectoring, you control only 2 degrees of freedom. And
Yes.
as I understand, the swirl, the torque cannot be controlled. Is it correct?
Yes. Alors, we at the beginning we talked about this technology because of a need from the attitude control system of the spacecraft, especially in the geostationary orbit, because in geostationary orbit we don't use magneto-torquers. We can't use magneto-torquers, so reaction will need to be unloading. So for this kind of problems, for this reason, we think about trust vectoring devices. But yes, it depends. It depends, of course, from each mission.
Thank you.
Any other question from the audience? So I have a question. Oh, yeah, I have several questions, Alberto. I will start with one about the cold gas thruster that you previously showed. Can you comment a bit on the performances and also on the fuel?
Yes,
it's written here. I missed that.
Yes, it's a very it's a confidential activity for the moment. We can't say a lot about this now, but we work with different gases from xenon to argon to krypton. We would like to propose a product that is capable of to work with multiple gases today. And as I wrote, the target for us is a thrust between 2 millinewtons until 10 millinewtons.
Okay. Interesting. It's really small.
Yes. It's the goal.
Yeah.
I would say it's quite high.
Yes.
You mean the trust level, Christophe?
Yes. Generally, we speak in micronewton. Here, it's millinewton.
Yes. I wanted to include it in this presentation. Also, if it's not electric propulsion, micropropulsion, but for us, it's a way to complete the thrust range. If I can say this, sometimes we need for a mission more thrust. So for certain maneuver, for a specific maneuver, so we think today about this kind of solution. When the thrust of electric propulsion is not enough.
I see. Interesting. Alberto, I have another much more general question. Are there any relationships or joint work?
Sorry?
Stéphane, we did not hear you.
Between the CNES and I have connected problem.
You have some, yeah, I think so.
I lost you, Stéphane.
Yeah, no, but it's my internet connection. Also, we are on the CNRS campus. I was asking about possible or existing relationships or joint works between the CNES and all the space agency on the specific topic of micropropulsion.
Of course, we work a lot of CNES works a lot with other space agencies from ESA, of course, to NASA or to JAXA. In our specific topics, the field of micropropulsion, we work a lot with ESA. And with other agencies on specific project, especially. So we have, for example, scientific or research project that we develop where we develop a satellite platform with JAXA or with NASA, and on this kind of project we have a joint venture with other agencies, yes. But it depends from each specific project.
Okay, thanks a lot, Alberto. Are there any other questions from the audience before we end?
May I ask you a question?
Of course.
Yeah, sure.
Yeah, my name is Won-Ho Cho from Korea. My question can be a little bit embarrassing one, but you have been developing the micro Hall thrusters for many years, and I'm wondering if how low the power, how can I say, the Hall thruster for micropropulsion, with how low power can you think you can achieve? 10 watts or even 5 watts? I'm wondering.
It's a very, very, very interesting question. So today I really don't know. I think that I don't know. Maybe Stefan can answer the question better than me. Because he knows very well the subject. I don't know if there is a limit. I'm sure that maybe there is a physical limit, yes, but I don't know exactly where is this limit today.
I think you're right, Alberto. I mean, technologically speaking, there is, I think, no limitation, but the physics tells you that if you reduce the sizes, you're going to increase the losses. And at what point you won't be able, I think, to maintain the discharge unless you probably drive a huge amount of power into it. But I cannot give any number. Probably 1 watt would be feasible with very bad performances, of course, because of the many losses, very, very low thrust efficiency. So my feeling is that below a given power, maybe a few tenths of watt, this is certainly not the right technology in terms of thrust efficiency and probably lifetime. But
okay,
I'm wrong.
Yeah.
And also, maybe you know that if, for instance, maybe in that case, a wall-less old thruster could be maybe more interesting, because then you are not constrained by the wall anymore and by the surfaces. We could explore all those paths, of course.
Right.
What is your viewpoint on hope?
We have attempted like about 20 watt, or a little bit smaller than that. And of course, as you already mentioned, the thrust efficiency drops quite significantly because of the physical limitations. So I was wondering, any of the audiences attempted very low power Hall thruster?
So Paul mentioned before that at the beginning of ExoTrade, they had a very, very low power thruster. I think it was around 5 watt. But yeah, the performance were also very bad. And this is also probably one of the reasons why they went to higher power.
Right.
Yeah, and if I can make a comment also on that, my opinion is also that the question of lifetime is also important. Meaning that maybe you can operate the thruster, but if the losses on the walls are very strong, very high, then maybe the duration and the consequence on the wall could be very dramatic. And finally, I mean, for commercial operation, for example, I think it could be a limitation. Yeah, at very low power, and there is maybe other concepts which are maybe more preferable, I would say.
Hey guys, it's
Hey,
Igal
Igal.
here. Hi. So I was working on this for some time now. We developed the concept, I think, around 6 years ago, 5 years ago. Developed a working model, 15 watt thruster, 20 watt. We got performance that is, let's say, thrust to power ratio of a standard hole thruster, so about 50 micronewton per watt. But of course, you have to pay somewhere. The losses are greater, of course, efficiency is lower. But I think this is also a path. So we can sustain at least thrust to power ratio like a standard thruster, even at 20, 15 watts. But this requires a very radical design change. So I don't know if we can call it a hole thruster even. So what we did is we created a very narrow channel, about 1 millimeter wide. Unfortunately, I will not be talking about this in this conference, but you can check it out. It's called narrow channel hole thruster. But you have to pay somewhere. You pay in ISP, basically.
Okay, thank you, Igor.
Thanks a lot, Igal, for your comment. So now it's time to close this first session with invited lecturers. So I really would like to thank again warmly our two speakers, Paul Lascombe from Exotrain and Alberto Rossi from the French Space Agency. Thanks a lot. The talks were really, really great. We all learned a lot, and I think they were very appreciated by the audience.
Thank you.
Time for a break. We will have a 15-minute break, and then we will all restart at 11 a.m. So in 15 minutes. I see you then. Enjoy your coffee. So welcome back, everybody. I think it will be time to restart the second part of the first session. We have 4 papers this morning. Let me check if all the speakers are in the list. George is already there. Igal is there. We miss Roman. Checking.
Stefan, Roman is in the, I think he's in the spectator. So,
Yeah, I moved him in
yeah, okay.
the panelist.
Okay, great.
He should appear in the panelist now. Yes, he is. And Igal was, so maybe he left and be back. Igal was already the panelist. So, okay, now it's time to start the second part of the first session with 4 talks. We'll have 1 talk, the first one about low power cathode, and 3 other talks about vacuum arc thruster. So the first speaker of this second part will be Georges Potrivito from the NTU in Singapore. And before Georges starts his paper, I just would like to say that Georges is the winner of the inaugural IEPC summer student competition. So he finished first. There were 60 PhD students in the competition. It was a hard competition, but we had really, really great work, great paper, and the committee and the jury decided that George was the first with a talk on cathode. So congratulations again, George. This was really, really amazing what you have presented. So of course, I expect a super talk also today. But it will for sure. So George, you've got 15 minutes. Okay, I tell you when you have 2 minutes left, and then
can you see my screen properly? Or?
Yes, we do. And I give you a sign, and after your talk, we will have 5 minutes of question and discussion. Okay.
Okay.
It's up to you, George.
Thank you very much, Stefan. Well, today the talk is not going to be on the same topic as it was for the IAPC, also related to low power cathodes, but today I will try to present a phenomenological approach for modeling a thermionic cathode with an open emitter with an orifice keeper. So I'm George, a final year PhD candidate at Nanyang Technological University in Singapore. This is the agenda of my talk. I will start briefly by presenting the existing zero-dimensional models and the main assumptions that were used over the years in building up such models. I will continue then with a description of the current model, talking about the neutral flow and plasma modeling, and as well as how the algorithm is implemented and which are the main parameters that the code can output. The third part is dedicated to results. And in the end, I will try to conclude my talk with some ideas for future improvements for the code. Well, the first complex phenomenological model for the emitter region of dispenser cathodes was developed in the 80s by Siegfried and Wilbur. They also came up back then with a definition for the effective emission length of the emitter as a multiple of the mean free path of the electrons. In the 90s, there were several codes that were developed for both orifice and the insert region of hollow cathodes, and notable examples are the codes of Capacci and the Moncos at the end of the decade. Such codes actually computed Such codes, they actually compute 3 main equations in each of the regions. So we are speaking about the ion mass, current, and power conservation equations in order to find out the plasma properties and make an approximation on the cathode operational characteristics. In 2008, Goebel and Katz provided a more sophisticated version of a zero-dimensional code. They used ambipolar diffusion to model the ion conservation. And also they came up with a very fancy way of treating the effective emission length of the emitter proportional to the e-folding distance of the plasma density along the emitter. More recently, the codes of Albertoni, Pedrini, Panelli, and Curciulo, surprisingly all Italians, they are more or less based on the codes of Capacci and de Moncos, solving for the same three main equations. And some codes are taking into account both electron and ion contributions, such as the code of Curciulo, or the cathode to Keeper gap region as the code of Panelli. Those are the main assumptions that most of the zero-dimensional codes are making, while the graphic shows the general geometry of an orifaced hollow cathode with its main dimensions. In most of the codes, the neutral flow is usually considered as continuous, which is not really the case in reality. We have a transitional flow, and it is modeled using Poiseuille's law. The plasma is treated as a three-species fluid with quasi-neutrality assumed. The heavy species, ions and electrons, are usually considered in thermal equilibrium with each other, and their temperature is either taken as equal to the wall temperature or much higher than the wall temperature. There are three main regions that are usually modeled: the insert, the orifice, and the cathode Keeper gap, where the plasma property is volume averaged. For the orifice, for the open-end emitter cathodes, the orifice plate doesn't exist anymore, and therefore the Keeper orifice region becomes more important as well. The plume region most of the time is ignored in this kind of phenomenological approaches due to the large volume of this region that calls for at least one-dimensional model, and also by assuming that in a perfect operation of the cathode in spot mode, the ohmic loss and the anode sheet losses are pretty small. But this is not true in the plume mode, for instance. Also, between the regions, usually we are modeling double sheets when the plasma with different properties meet. Right, the PSAC-KE cathode is actually an open-end emitter orifice Keeper cathode based on an LAB6 emitter, lanthanum hexaboride, that was developed at our institute and extensively tested with krypton. But therefore, it was necessary to model the plasma in such a cathode geometry, given that none of the previous models achieved this. You can see on the left-hand side the main the general model with the three regions highlighted and their main dimensions, while the plasma property in terms of electron density, electron temperature, and sheet potential is computed in each region. The model starts with computing the neutral pressure in the three regions, while the state equation is used to make an estimation of the neutral density. In terms of temperatures for the neutrals, in the Keeper orifice, we consider the temperature of around 1000 Kelvin, which is a experimentally found temperature for sub-ampere cathodes, while in the insert, the temperature of the neutrals is taken equal to the temperature of the insert, found based on the emission current by applying the Richardson equation for thermionic emission. We also came up with a very handy equation for krypton dynamic viscosity, something that it's we couldn't find it in literature based on experimental data, and we tried to make the formulation of this equation very similar to the one of Xenon. An important step is setting up the current continuity model. In other words, defining every single current that passes through and from each region, as well as to model the two double sheets. We are modeling one double sheet between downstream of the emitter, between the emitter and the cathode Keeper gap, and another double sheet between the cathode Keeper gap and the orifice. We consider the thermal equilibrium for the heavy species and their temperature equal to the wall temperature. In terms of emitted current, we used Richardson thermionic emission equation with the Schottky addition based on the electric field, the local electric field, where the work function for the LAB6 is treated as a function of wall temperature. In terms of the effective emission length, we considered it proportional to the internal pressure as suggested by Albertoni, an equation which scales pretty nicely with many cathodes, especially for open-end emitter cathodes. And the K parameter, which is a proportionality parameter, should vary between 5 and 15. The double sheet, both double sheets are modeled as planar, while the voltage drop across the double sheet, we use this formulation given by Capacci. Given the neutral density inside the three regions at the mass flow rates that we are usually testing our cathodes for, and the characteristics dimension, the characteristics lengths of those three regions, we can say that the plasma is optically thick at the excitation wavelengths for krypton and xenon, and therefore any excitation losses are ignored in the following calculations. So this slide actually summarizes all the three main equations that are iteratively solved in each region in order to find the density, the temperature, and the sheet potential in the end. For the current continuity, the models that I presented in the previous slides are used, while each current is carefully defined either as an IF flux through a sheet at the wall or through double sheet, or thermal random ion and electron fluxes. In addition, the emitted current is a model, as I said before, using Richardson equation. Next, ion production through the volume ionization at a specific reaction rate is balanced by ions loss at the walls or outside the volume through the double sheet, or a simple thermal flux. Finally, the Joule heating is the main power source for the plasma heating, as well as extra power brought in by incoming electrons and ions through convection. And this, the plasma is actually cooled by ionization, and also ions and electrons lost to the walls or through the double sheets in the other regions. We managed also to set up two handy relations for the ionization and excitation reaction rates for krypton, since the literature lacks this kind of data for this particular gas. Of course, the data for the cross sections was taken from the literature, and we just fitted it to look nicely like the ones we have for krypton. For xenon, sorry, and also for the neutral scattering cross section, which is not shown here, but it's important for computing the plasma resistivity. So the model is actually initialized with geometrical and operational parameters, and also some assumptions on density, temperature, and potential. And after the neutral density is calculated and the effective emission length is estimated, the external loop starts with the Keeper orifice, then the cathode Keeper gap, and then the insert. We solve iteratively the three equations in each of the regions, and the model will converge when the results are within a specific error coefficient. Besides the plasma property, the model outputs also the discharge power as a sum of three main classes of powers. We're speaking about the power to accelerate thermionic electrons through the sheet, ohmic heating in each region, and also the power lost through the two double sheets. By knowing the discharge power and, of course, the discharge current, one can find the discharge potential, which is also experimentally found. Time for some results. The first comparison is with our cathode, run with krypton at currents less than 1 ampere. As you can see, the model manages to predict the trend and the magnitude of the discharge potential within 6 volts of difference. However, for this, we use the K parameter around 3 meter Pascal, which is much lower than the theoretical value. And we believe that this might be because either the internal pressure, definitely the internal pressure in such an open-end emitter cathode is much lower than for the orifice cathodes, and therefore a large K will lead to a longer emission length. Or another possibility is that the potential drop in the plume, which we are ignoring, can account for a considerable percentage of the total discharge power, discharge potential and discharge power implicitly. When looking at the different discharge power distribution, we observe that the sheet power remains the main contributor, and while the ohmic power is pretty low, which comes in a contradiction to the orifice cathodes, where the ohmic power is pretty high, especially in the Keeper, especially in the orifice, and contributes substantially to the self-heating mechanism of the cathode. The double sheet power also increases with the discharge current due to the larger currents that pass through the sheets. Another comparison was made with a higher current cathode to see if the code can predict results for higher currents. Also open-end emitter cathode, heaterless this time. The currents for up to 30 ampere. The model overpredicts the discharge potential, but within a reasonable gap, and we used the K parameter very close to the theoretical value. And this might be to the fact that this time the internal pressure is pretty high, and we are using the xenon instead of krypton. When the mass
2 minutes left, Georges.
How many?
2.
Okay, then probably I will skip this and go to the geometry exploration. Here, what you can see is that the results when the Keeper orifice or the emitter, the Keeper orifice is decreased or the emitter length is increased, a very important drastic influence on the cathode. We can observe a drastic influence on the cathode power, and this is because we are playing actually with the internal pressure. And since the internal pressure increases at the K being constant, the emission length will decrease. And when the emission length decreases, the emitted current also decreases. And the only way to balance such a small emitted current, more ions have to go to the emitter surface. This will call for a higher shift potential and therefore higher power. Now, this is also important, the power budget. We can see that the main heating mechanism for such an open-end emitter cathode is ion flux to the lateral surface of the emitter and not ohmic heating from the orifice. The electron contribution is pretty negligible, and also we can have a huge contribution with redeposited power from ionization events and also thermal fluxes of ions from the different regions. So I presented today a zero-dimensional plasma model for a specific type of cathode with an open-end emitter and orifice keeper. The code models 3 regions and 2 planar sheets, while both ion and electron contributions are considered. The effective emission length is taken as proportional to the internal pressure, and the krypton is used as gas while providing handy formulations in terms of dynamic viscosity, ionization, excitation, and scattering cross sections. There was a good agreement between the modeled results and the experimental data for both xenon and krypton-fed cathodes, while for krypton at low mass flow rates, the K parameter tended to be very, very low as compared to the theoretical value. The model predicts that such cathodes are characterized by large shift potentials, and the main heating mechanism is ion flux to the cathode surface, whereas the ohmic heating is pretty negligible. In the future, the plasma code can be coupled with a thermal model, while the temperature of the heavy species can be assumed as higher than the wall temperature. Thank you very much for your attention. If you have any questions, I would be pleased to answer.
Thanks a lot, George. It was again a very interesting and impressive paper about low current, low power cathode, and I know how difficult it is. So do we have any questions from the audience? Please, we still have 2-3 minutes. So we start. Why did you decide first, George, to go with krypton?
Well, the idea of krypton, well, the fact that first of all, it's a much cheaper propellant, and but this is not the main idea for us as a laboratory, because it doesn't really matter. But we observed and we believe that in the future, with all the deployment of large constellations, and if we look at SpaceX, all their thrusters are based on krypton. Such actors can do a lot of saving by using krypton instead of xenon. Therefore, I believe that I know that krypton is not the most appealing gas to have extraordinary performances with both thrusters and cathodes. But I believe we should consider this propellant more and more, because we can save costs and we can offer to the industry solutions that are can work with much less costs than xenon. Therefore, optimizing the cathode that works with krypton it was of high interest for us.
What about your feeling between krypton and xenon for cathode? I mean, if let's say if a cathode is optimized for xenon and
I think you're breaking up, Stefan. Probably the internet back there at the car is not the best today. So you are talking if it's optimized for krypton, what's happening if I want to use it with xenon? It works perfectly. I mean, there is not much of a material interactions, and we are using lanthanum hexaboride, which is pretty robust for with interaction with most of the inert gases. So there is no problem with that.
Thanks a lot.
Of course, xenon is going to improve the characteristics. For instance, the coupling voltage becomes lower, and it's better, of course. But we try to do as much as possible to maintain the coupling voltage as low as possible when using krypton. If you use xenon, it's even better, but krypton would be the choice.
And do you think, you have a last question? Oh, there is a question, I think, from the audience. Let me check. It's about the point heating, but from Timothy Ebner.
Yes, I mean, the question is, have you considered in your model only, I mean, have you included anomalous effects like ion acoustic turbulence, you know, kind of ion acoustic instability that we can observe in some cathode?
No. I mean, it's a very simple simple
It's
model.
a classical description of
exactly.
Yeah,
it's
okay.
a classical description. And I mean, the model, of course, you can use the model, for instance, to predict at the limit, for instance, the spot mode transition. If you look at how much thermal flux the keeper electrode receives in comparison with the total discharge current and things like that, you make a ratio like it was proposed by Mandel and Katz at the beginning of the 90s. But of course, this is in order to include all those things. Like ion acoustic turbulence, you need a proper 2D model or at least a 1D model. I think that the anomalous I think it's hard. It's hard to include it in such a phenomenological model.
Yeah, thanks, George. I finally got myself unmuted here. I guess what I was trying to ask here is whether or not the inclusion of maybe that anomalously high collision frequency might change kind of the power balance here, to be something where like the ohmic heating might actually be significant compared to the ion power loss to the walls.
Okay. From this point of view, yes, that might be the case. I think, yeah, probably the anomalous collision frequency, a model for it at least. I think can be included definitely in the definition of collisionality, and see if it changes the results very much.
Sure, thanks, and great talk.
Sorry to interrupt. It's time to stop this discussion about the cathode, but of course you can.
Thank you.
Online. Thanks again, George. Now we're gonna move to the next speaker.
Let me stop the sharing.
Okay. Roman. Yes, so the next speaker is Roman Forster from the Military University of Munich. Roman is going to talk about the AirVat thruster. So I leave the floor to you. You've got 15 minutes, Roman.
Yes, okay. Do you hear me?
Yes, we hear you.
Okay. I see the sun is shining in my office.
Yeah, it is. This sunshine in Munich.
Okay, let me share the screen. Okay, normally you should see my presentation.
Yes, we see it. Perfect.
Okay.
You can start when you want.
Yeah, wait a second. So I make this. Okay, so hello everybody. My name is Roman Forster. I'm a PhD student at the Bundeswehr-Universität München, and I will show you our work on the development of the HERVAT electric system for a 1U CubeSat. First of all, short guidance for you for the next few minutes. I will explain this, the new system for you, the thruster head and the corresponding power processing unit. And after that, I give a little bit information about the characterization and description about regarding the performance and the dimension of the system. And after that, some information about the adaptations for the system to integrate into a CubeSat. And at the end, I will give some possible or potential improvements and a short outlook for the future. So maybe some of you will think, what does HERVAT actually mean? HERVAT is it's only a shortcut for a high efficient and reliable vacuum arc thruster. The word HERVAT includes the thruster head itself
and the corresponding power processing unit. In a lot of previous laboratory tests, the system has generated over 10 million pulses, very reliable. And the high advantage of our system, of the Harvard system, is its simplicity, because we don't need any additional system like feeding mechanism or so. And it's also good applicable for small satellite systems. Here you see a schematic draw of our thruster head. The thruster head consists basically of 2 anodes and 1 cathode. Here in the middle, the red one is the so-called auxiliary anode. It's made of copper, and the blue one, the blue one is the titanium cathode. The cathode is cup-like formed, and the yellow so-called ignition anode at the outside of the thruster head is separated from the cathode by an insulator. And you also see here in the draw that we have a small gap between our cathode and the ignition anode. The gap is 0.4 millimeters big or small. And so you can polish it with graphite powder or something like this for ensuring to have better starting condition for the triggerless mode. But we also have detected in our tests that for our system we don't need that starting condition. The auxiliary anode is also, as additional information, is fixed by peak holder, and a big part of this auxiliary anode is shielded by a thin ceramic tube. In this slide, you see the corresponding power processing unit. We have 2 different voltage levels. On the left side, U1, and on the right side, U2 for the 2 different capacitors. So you can call it, it's a kind of dual stage capacitor energy storage. And this PPU has the ability to switch automatically itself between the triggerless or trigger mode. We have in the system also a high voltage generator, and this high voltage generator is responsible for the trigger mode. And we have also here a CDAC. CDAC is the shortcut for a silicon diode, which in this case for alternating current. And the CDAC is responsible for a well-known triggerless mode. You see also both anodes are connected in parallel to our PPU. In this slide, you see the measurement of 1 pulse of the PPU or of the Harvard system. In this case, it's a high voltage. The ignition was a high voltage trigger mode. It's clearly see because of the high voltage peak here in the yellow line, and then so in the green line, and it's the thruster voltage. And you see also the purple lines that we worked with a voltage level of about 240 volts. And in the diagram below, you see the current of the both anodes. The blue one is the ignition anode and the red one auxiliary. We measured the current of up to 90 ampere with the ignition anode, and for about 50 ampere at the auxiliary anode. Some words about the characterization. As I mentioned before, we need 2 different voltage levels for our system, 95 volt and 240 volts. We have also 2 different capacitance levels. The second one, the 4.7, it's not changeable. We have done several tests,
and we have reached the best performance with this value. But the capacitance of the first capacitor is, of course, changeable. It depends on the pulse length you want to create. This supply gives us an output, as I mentioned, a high voltage peak from the range from 0 to 10 kilovolt, and the mentioned current. And this leads to a pulse of the pulse length can vary between in a range of 20 to 100 microseconds, and has an energy of 0.7 joule. And we operated with the system with a frequency of between 1 to 5 hertz. Then some words about the performance of the system. As I mentioned at the beginning, we reached more than 10 million pulses, very reliable. And in that long time measurements, we have detected a mass loss in the range between 0.4 and 1.2 gram. So we have calculated an ejection rate for about 15 microgram per coulomb, and the thrust to power ratio of the Hertz system is 1.5 micronewton per watt. Here for you, only for your imagination, that the currently laboratory prototypes on the left side, our PPU, currently the size of 18 to 15 millimeters, and on the right side you see a thruster head, which has currently a total mass for about 45 gram. Some well-known additional information about the requirements of a 1U CubeSat. So I think I can go a little bit faster through this slide. We have the space dimension, and then the requirement regarding the mass, the voltage levels, and also the power we can require. So what have we to do for adaptation, for integrating our system to CubeSat? First of all, we have to replace our not space-proven parts against qualified parts. This can be done by the by the appropriate qualified parts. We have also to decrease the size of our system. It can be easily done by using the SMT technique, of course, the qualified parts. It's also space for improving or optimizing the geometry of the thruster head and also of the size of the PPU. Then we need our required voltage levels of the CubeSat. So this can be, I think, easily done with the usually step-up converters, as previous missions have showed. Then of course we have to do it in this case for our voltage levels, but the principle is the same. And after that we have to check our EMC. This would be done by the corresponding tests, and if necessary we have to shield our system. Of course, there are also space for potential improvements. One possibility is to integrate an active triggering system. The current state is that the system as itself switches automatically between the triggerless or trigger mode, so that we have the possibility to manipulate it by our own. We also can add a magnetic nozzle for improving the thrust of the system. A nice improvement would be to control the pulse length via maybe a microcontroller, to extend our pulse length and so on, our thrust. And also a good idea would be to integrate a pulse detection system, whether we can realize or control if ignition was taking place or not. And yeah, at the end, I will give you a short summary or outlook. What have we done? We have developed a very good system which produces us a lot of post counts. That's the system Harvard. In several long time tests, it was extremely reliable. And now our work in progress is to adapt it or to integrate it into the CubeSat. This is the task we are now in progress. And after that, we have to do the mentioned CubeSat tests. And this will be next step. And then, yeah, I think hopefully we will have a successful mission, but that's yeah, a dream for the future. That was my presentation about our Harvard system. Thanks for your attention, and yeah, feel free for questions.
Thanks a lot, Roman. Very good job.
So. Okay.
It's very impressive number. So I already have in that case, are you expecting any issue with the onboard electronics? Did you hear the question?
No, I didn't hear it. Can you repeat it, please?
Oh, yes. So Daniel Peregrande from United Space is asking if you plan to operate the thruster at 10 kilovolt in the future IOD model. And if so, do you expect any issue with the onboard electronics?
Problems regarding the high voltage?
Yes.
Yeah, that will show the future tests. But in our previous tests, I think that would not be the problem, because the highest voltage peak we detected was about 3 kilovolt. The high voltage generator is only able to perform until to 10 kilovolts, but it depends on the conductive layer, which is very different the whole time. But as we've seen in our long time tests, it go very fast, and then the high voltage peak goes up to 1 or 1.5 kilovolt. That's the highest amount.
So Daniel, do you want to comment on the answer? We don't hear you, Daniel.
Yeah, can you hear me now?
Yeah, it's better.
Yeah, no, that was fine. That was just I was just wondering if that was 10 kV was since that's what came up in the presentation, whether that's what the operating voltage was. But no, just in general, like there's obviously issues in power electronics, especially if you're using things like MOSFETs and so on regarding high voltages. So just something to keep in mind. But I think if your highest voltages are around 1.5 to 3 kV, that should be doable for kind of space electronics.
Okay, thanks, Daniel. Ashley, you can ask your question yourself if you want. Oh, I don't know if Ashley is hearing me.
No question.
Can you hear me now?
Yes.
Yeah, we can.
My question was, have you characterized the microparticle generation from the thruster?
No, not yet. That's in progress. So it's a pity that I can't say you exactly characterization.
Do you have any idea? Maximum diameter, range, any information?
Yeah, hard to say. We have also made several tests with a magnetic nozzle where we can, of course, decrease the
the size of the microparticles, but yeah, to say exactly size of it, it's at the moment it's hard to do for us.
Okay, thanks.
Sorry, yeah, sorry.
Thanks a lot, Ashley. Are there any other questions from the audience? Roman, I just have a question. I was really impressed by the number of pulse of your VAT. Of course, you said it's more than 10 millions.
Yes.
Maybe I have missed it, but can you give us the total impulse then that you can achieve?
What was the last sentence? I didn't understand it right.
Sorry. In that case, what is the total impulse of your thruster?
The total impulse I have to look or
because it's an interesting quantity, of course.
Yeah. I haven't the exact value in mind. I think I have to search it, but I can send you the information if you like.
Yeah, with pleasure.
Before I will tell something wrong.
No, let's do that.
But in the paper, I think it's mentioned, and I can send it to you.
Okay, great. Let's do that.
Yeah. Okay.
Okay. Thank you, Roman, for your interesting paper about the hair VAT. So now we to move to the next speaker. And the next one is Igal Kronos from Technio in Israel. So Roman, you can just, yeah, okay, perfect.
Yep.
Igal, I don't see you. We lost Igal. Strange.
He is in a spectator.
I don't see him.
Yeah, at the.
Okay. Let's sorry, Igor. I will move you back to the speaker list. So now you're in the speaker list.
Hello, can you hear me? Can you see me?
Yes, here you are. Sorry, it's my fault.
Thank you. Just a moment. Can you see my full screen now?
Yes, we can.
Great. So yeah, so welcome everybody and to this interesting session. And we had already a presentation about vacuum arc thruster. I'm going to continue and show you an alternative way of getting a lot of pulses. So we're going to discuss testing and validation of vacuum arc thrusters with active feeding. Okay, this work was done for the past 6 years already with a number of colleagues here. I can mention Dr. Satyajit Choudhury, Matteo Laterza, and others. And we basically, yeah, we're working quite a lot of time on this, how to make a long duration vacuum arc thruster. So I will give some introduction about vacuum arc thruster. I think maybe some people will be interested in that. Then I will speak about our inline screw feeding system for this long duration thruster. And then the main course will be the lifetime measurement and maybe some words about the mission that we're going to fly. Okay, so vacuum arc thrusters are basically pulse DC discharges that produce thrust based on ablation of solid metal. The vacuum arc, it burns basically in the metal vapor because it operates in vacuum. So it burns through the metal vapor of the cathode itself. This is the medium for the discharge. And the combination of Joule heating and the ion bombardment on the cathode basically heats it and maintains the temperature to emit electrons and vaporize the cathode material. This produces high velocity, highly ionized metal plasma flows. And there is essentially no need for external magnetic field. We can, of course, edit because it's a plasma system, but it's not a requirement. And the discharge is maintained, this is very interesting physics, through very small mobile spots on the cathode. So this is like a very basic drawing. So we have a cathode, we have the anode here, some insulating material, then the discharges are happening on the surface, and the cathode itself basically bursts and from these burst material from these spots. They are micrometer sized and basically consume the cathode. And we have this interesting phenomena of cathode motion, spot motion. So we can observe over time how this area of emission basically changes, because one spot dies, the new spot form, and so forth. Each spot can maintain around 100 amps. And since this spot is like a micrometer size, it's a very interesting device or potential physics for microthrusters. So, as I said, we can produce from these explosions, micro explosions, this metal plasma, highly ionized, usually twice or three times ionized. And so close to the surface, we have very high density, around solid density, and then it drops as it expands. Typically, we get quasi-cosine distribution of the plume, and which direct perpendicular to the metal surface. We get velocities of around 10, usually 20 kilometers per second for the ions, and around 10% of the discharge is carried by ions. So this is the physics of this process in a nutshell. But there was an interesting technical development already almost 20 years ago, that we can ignite these discharges using relatively low voltages. If we use this triggerless mechanism, where we basically contaminate the insulator and create a pathway to ignite the main discharge using these the film. We basically provide some sort of coating of film or metal film on the surface. This film can be ignited. Basically, the particles create small plasma, and then it creates the pathway for the main discharge. And this allows us to basically ignite it at relatively low voltages of a couple of hundreds of volts. So this is a really interesting process, but it requires this coating and sustaining this coating. Otherwise, you will not be able to ignite. So from our experience, what we saw is that when we operate these kind of coaxial devices, we cannot sustain many pulses, around tens of thousands, using this triggerless technique. Usually it's associated with changes of geometry. The cathode is being eroded, and also, very importantly, is the insulator is not coated sufficiently. So we need to reheal basically, or redeposit this layer constantly in order to maintain good pulse-to-pulse ignition. So this classical device, the one that, as I showed you 20 years ago, does not meet propulsion requirements as it is, because of the limited pulses. So what we did is basically to use the same kind of geometry, because we like it. It provides, we'll show the numbers later. And we want to basically mitigate the issue of erosion as much as possible, if at all. So what we did is created this screw feeding mechanism. I don't want to go into all the details, but basically we have a screw, and the cathode is connected to the screw, and we turn this in a specific ratio, a specific rate, and we get a helical motion of the cathode. So it's not only going out in a straight way, but it's a helical motion, like exactly as a screw. And what we saw is this allows us to create uniform erosion, and even mitigate by advancing it, mitigate cathode erosion, and sustaining therefore the performance, pulse-to-pulse performance over many, many hundreds of thousands of pulses. And the mechanism is quite simple. It's just a screw, yeah. So you can look here at this, for example, paper. So basically, what we operate usually in our lab, the Technion, is hundreds of thousands of pulses automatically. I will show you a short video soon. And this is how it looks like, basically taking a picture under a microscope of the front of the thruster. You can see the dimensions. It's basically less than a 1 millimeter device. and this is the initial condition, the clean condition, and this is after about 400,000 pulses. And this is actually a very nice picture because you can see uniform erosion, and that you can see that the cathode basically is maintained in the same position. So we are essentially maintaining the geometry, and you will see later that also the performance is able to be maintained. And so this is our thruster. It's basically a flight prototype. This is our performance figures without any external magnetic fields. I want to mention again, and the fuel is integrated inside this device. So this is our thrust to power ratio, specific impulse, total power is less than 2 watt. This is for the arc power, what we call the arc power. Total impulse is this number, and you can see dimensions are very small. And remember that the fuel is integrated inside the thruster itself. So around this, we built a propulsion module. You can see it here. It has electronics, a PPU system that not only provides for the power conditioning, of course, but also for the active feeding and control and timing functions. So everything is integrated in one small card. The electrical scheme is very simple. It's just one coil and one IGBT. And this is the flight model's parameters, voltages, power level. This is the actual input level for the whole system, dimensions, and so on. So we typically operate it for 1 day, continuous. So, and our test system is a small chamber, and this is something that I really like about these microthrusters. We need a very small chamber. With 2 turbo pumps, we can get 10 to the minus 6 millibars and easily in 20 minutes. And we have a thrust balance, micronewton resolution thrust balance, and on it we place the module, continue the whole thing, the thruster and the electronics. We have a Pearson coil for arc current measurement inside, and that's basically what we have inside the vacuum chamber. Outside we have electrical diagnostics, so like the input current and also the digital to analog, analog to digital sampling system. So this is like raw data that we get from a measurement. So this is the input current. You can see we have this initial stage. There's a small power dedicated for advance because we need to release the screw. It takes a little bit of power, like around 200 milliwatt for a few seconds. And then we have the actual operation of the arc. You can see here a picture. I'll show you the video as well. And then basically we give the system to cool down because, as I showed you, it's 90% is heat on the anode. So basically we have to let it cool, and then we have so about 90 seconds, 90-second operation, 5 minutes of cool down, and then we repeat this for thousands and thousands of times. The thrust, as you can see here, is typical as well, and it follows quite well with the discharge. Yeah, so I want to show you the video. So just a second, I will have to stop this share, and I'll share another window. Just a second. Can you see this picture here?
Yes.
Okay, so I'm playing it now. What you see here is an accelerated about 3 or 4, I don't remember exactly, 4 hours of operation, and it's accelerated 40 times. So you will see the plume and then the advance on the backside. So the plume. Let me just, I don't know how the quality of the video feed.
Not very well on my side.
It looks well, good. And you can see not well. It's not, doesn't look well. Well, okay, so let's try again. We'll try again. Okay, now it's better.
Better, yes, yes.
Good. So you can see the plume. Then you can see the advance on the backside, and it's a repeatable automatic process. We have a microcontroller that does this timing system, and you will see that there is a firing, and then there is advance, a firing, and then advance, and that's it. And this is operating for 24 hours, and then we can all take all the characteristics. Okay, I think I can close it now. I'll go back to the slides. Yeah. Okay, so let's talk about diagnostics a bit, because this is very interesting, how you do a pulse system diagnostics. So what we do, we have R current measurement and input current measurement for the PPU. And we use different digital to analog to digital sampling systems. So for the input current, we just have a whole current monitor on a simple DAC. On the ARC, because we need the resolution, the time resolution of the ARC itself, which is around 100 microseconds, we cannot use the DAC, so we use a scope, a PC controlled scope, and then we can get all the data we want. So it takes you hundreds of megabytes of RAM, not hundred, but tens of megabytes of RAMs on the scope, and then we can analyze it. Okay, so this is a simple one pulse measurement of the scope, and you can see the arc in black, and the current in black, and the voltage in red. As you can see, we have around here in this case 40 amp peak, and then it drops in a triangular kind of shape. Voltage is maintained around 30, 40-ish volts. This is typical for an arc. Yeah, and you can also read about this in this open access paper if you're interested. So what we have to do is basically take these very narrow pulses, and then we want to test the lifetime. So what we have to do, we have to go through 2 more time scales, basically. So we have the 100 microsecond time scale for individual pulse. Then we have a 90-second time scale, seconds time scales for the actual firing packet. And then we have, you know, this 24 hours time for capturing the whole thing. So what you see here is this, as I mentioned, 5 megapoints. This is the integrated arc, individual arc current multiplied by voltage, and you can get the power. So you see here in red, basically how the power behaves during these 80-ish second of arc. You can see in blue the thrust. And again, you can see that it follows very well. So we get very high confidence. We don't need the thrust balance, basically. We can track just the power, just the current. And in red, you can see this is our PPU efficiency, which is around 40% at this point. But of course, we can get 90% if we invest in electronics. But this is the current state. So now we want to characterize this over, as I said, hours and so forth. So what
1 minute left, Igal.
Yeah, thank you. I will hurry here. So basically, the way we do it is we quantify the charge per pulse, and just the integration of the R current. And this is we get the statistics of about 1,500 pulses for each firing packet. And you can see this kind of Gaussian distribution with millicoulomb per pulse. And you can see that from 0 turn to 10 turns, there's not much change. And also at the end of lifetime, also very similar. So we are quite happy about this result. You can see the numbers here, millijoule per pulse, the voltage, and the time, and the millicoulomb per pulse. So this is the final integration. As you can see, these are basically all the packets we fire. We fire, as I said, 80 seconds, about 1,500 firings of pulses per packet. And we fire them for hundreds of packets. And this is how it looks, the evolution of the average power and the PPU power. And we consume about 22 milligrams of cathode in this about 20 hours of operation. Yeah, and I will skip the experiment. Yeah, so I think I'm finished. So Stefan, if we have time, I can talk about the slides of the mission as well.
No, we don't.
Okay, so
we won't have time for any questions. Thanks a lot, Igor, for this very interesting talk about that, which is a different approach compared to the AirVat. Are there any questions from the audience? We'll have a few minutes. I have Igal. So finally, now the limiting factor in your case is the anode. And we are of the anode.
You want to see this picture here?
Yeah.
Okay. Well, it's an eroding thruster. We consume everything. Consume the cathode. We consume the insulator. We consume the anode. Right. So basically, the design calls for the erosion. Basically, you have to match the erosion rate of the entire system. Once you do that, you know the lifetime. But it's not an endless thruster. So I believe that this, like thruster head, which is, you see that it's tiny, it's like 1.5 millimeter in diameter. It can sustain 24 hours operation, 0.2, 0.3 Newton seconds. If you want more, then you just use many more heads.
Okay, this is the strategy. Okay.
Or another approach is to change the geometry, which is the interesting thing, is to get the scaling laws, because we use the smallest possible kind of cathode, 0.8 millimeter diameter. But probably if we use a thicker one, we can get much higher total impulses. But then the geometry will change, and this requires, we need a full-scale understanding of this erosion patterns, and of course, this is a huge effort.
I understand.
So I hope this is a start.
Did you also try the various material for the cathode?
Yes, we of course can consume any metal, but we found that titanium, in our case, produces the right combination of melting and erosion that provides us the coating. It's very important, and the lifetime, and it gets good performance. So yeah, we can use different materials, but the titanium works well for us. So,
Stefan, can I ask?
Of course.
Yeah. No, I got it. So when you show the average charge in your at the end of your talk, so it was with titanium, yes?
Yes.
As material. Okay.
Right. So all the experiments I showed you were done using titanium.
Okay. Okay. Thanks.
Right.
There is also a question from Christophe Coppel.
Go ahead.
Yes. Hello, Igal.
Hi.
I want to speak about the efficiency of your PPU. It's strange. You have an input of 6 watts, but in the arc you have only 2 watts. So what about the 60% of the power?
This is just electronics. I needed to hire a better engineer. Sorry, I need a better engineer. Well, that's all I can say. This is just pure, really, just design.
Okay,
we should get around 90%. We should get around 90%.
Yeah.
So there's a lot of room to.
It was indeed a very good question, and I didn't expect this answer. Thanks, Igal. Okay, thank you, Igal, very much for this very interesting paper. So now it's time to move to the next speaker. So the next speaker is Etienne Michaud from the iCare Laboratory. And it's again,
hi, everyone.
Etienne, it's again a paper on vacuum arc thruster. Okay, so Etienne, it's up to you.
So can you hear me?
Yes.
Yes, can you see me? No?
Yes, we can.
Yes, okay, perfect. So let me share my screen. You can see it, right?
Yes.
Okay, perfect. So good morning, everyone. My name is Etienne Michaud, and I'm working as a research engineer at the iCare Laboratory for the CNRS of Orléans, under the direction of Stéphane Mazouf. And this morning, I'm going to talk about the plasma parameters in the plume of a low-power vacuum arc thruster. So far, I think that you already know that the vacuum arc thruster is based on the ionization of solid propellant through an electrical vacuum arc. It's pulsed plasma from metallic elements, the element that compose the cathode. The expansion of the plasma can be free or through a magnetic nozzle, depending on the design, and that creates the thrust. And what is really interesting for this technology is that it shows interesting perspective concerning system miniaturization, because it ejects a quasi-neutral plasma, so you don't need to add any neutralizer to avoid the charge accumulation on the satellite. And it operates a solid propellant, so there is no need for a gas feeding system, neither for a propellant tank. And also it operates, there is a high density storing of this propellant. So all of this simple design goes to an easy miniaturization. But of course, there are some drawbacks of this technology. As Igal already mentioned,
the arc triggering is quite complicated, and it's also strongly related to the pollution of the insulators. As you are ejecting a metallic plasma, a metallic coating will appear after some pulses, and it's quite difficult. The vacuum arc physics are also quite difficult to handle for such high current that I will present later. And the cathode erosion is a really interesting problematic, as you need a constant gap between the cathode and the anode. To do so, you need to have an homogeneous erosion or feeding system to the anode, to the cathode. And all of this leads to an overall low lifetime, and so a low total impulse. We're talking about few kilonewton second for the most efficient, and a limited delta V. But all of this problematic can be, or at least part of this problematic can be solved with an increased research effort. So this is why the European Union founded the Plasma Jetpack project, coordinated by COMAT. You will have a talk a bit later with Antoine, which is at the head of this project. This is why I'm not going to talk that much about the characteristic of this vacuum arc thruster. All I can say so far is that it's 30 watt, 1U. It operates 250 volts between the cathode and the anode. For the experiment that I will present you, we have mounted a nickel and chromium cathode. It operates at the maximum current between the cathode and the anode between 3 and 6 kiloamperes for a mean thrust, or about 0.5 millinewtons, and an ISP around 2,500 seconds. Probably those values are a bit outdated, but what is really interesting is the arc triggering system, which apply dozens of kilovolts over 1 microsecond. And this is really interesting because this triggering system will show interesting results in the thing that I will present you. So to outline the plasma parameters in the plume, what we did is basically Langmuir probe measurements, which is an intrusive diagnosis method based on IV curve acquisition and analysis. Those measurements have been made with a cylindrical Langmuir probe made out of tungsten. You have the dimension here on the left. It was placed 20 centimeters away from the anode along the thruster center line. But the main difficulty for this was to scan the voltage during a single pulse, which is quite difficult. And for the accuracy of the results, it's not so easy, because during one pulse, the plasma parameter will evolve, and so you have to scan really, really fast to see the parameters and to get the IV curves. So what we did was acquire current traces for each bias voltage step. We averaged it over 20 pulses. So each voltage step, 20 pulses, a time average mean, so that we can have an overall behavior of the vacuum arc thruster. And then we have a lot of current traces. We fix the time, and then we are able to reconstruct the IV curve. Here, in this example, I show 10 microseconds, but there is also for 16.5 microseconds. And once we have that, it is possible to have the electron density, the electron temperature, and the plasma potential for a given time. So at each time step that we decide to analyze those curves. And to process this data, we use the three model, the OML, which is the more well-known and the more easy to apply, and then the ABR and the BRL. All of them differs in terms of assumptions. So what we have for the electron density is that we have a first density peak at 7 microseconds, which is in correlation with the triggering system. The triggering system is activated for only 1 microsecond, and it's the exact width of this first density peak. I show here in gray the discharge current. You can see it goes up to 4 kiloamperes. And after this first density peak, the density of the jet follows fairly accurately the discharge current waveform. So there is differences in magnitude between the model. It is normal as they are different in terms of assumption. I want to point out that the BRL model is the most complete, as it takes into account the formation of an absorption radius around the probe, depending on the bias voltage applied. It's based on the resolution of the Poisson's equation, and it takes also into account the ion angular momentum. So for the electron temperature, we have been able to see that at the beginning, at 7 microseconds, during the triggering discharge, it's a really hot. There is hot electrons, more than 25 eV, comparing to the rest of the pulse. And after that, there are fluctuations between 4 and 6 eV. So as there is higher voltage during the arc triggering, it's not really surprising that we have higher electron temperature at the beginning of the pulse. So before 5 microseconds, the model were not shown because there is too low signal to noise ratio. The probe is at 20 centimeters away of the anode, so few particles have the time to reach the probe. So after that, what is interesting to investigate is the velocity of the ions. So to make this, we did time of flight measurements based on two probes, a grid and a planar probe, 5 centimeters away from each other at a variable distance from the thruster, and equally biased, which is really important to avoid any acceleration between the grid and the planar probe. So when we trigger a pulse, first the jet hits the grid, it creates a trace on the oscilloscope, and then it hits the planar probe. So you have another trace on the oscilloscope, and doing seeing the time difference between the two, we are able to find the velocity of the jet. But the difficulty here is that there is multiple peaks, and those multiple peaks shows different velocities. So for a correlation analysis, it's quite difficult and even inaccurate. So what we did here is peak-to-peak time of flight. So comparing the time of occurrence of the first peak, then to the second, etc. Another difficult thing is that here I show you different ion current traces for coming from different pulses. You can see that there is often two peaks, but sometimes there are three, or sometimes there are only one. Here I do not show that. And why are there multiple peaks? It's quite unknown at the moment because those are preliminary results, but we can probably imagine that it's coming from ions of different masses or different acceleration processes, probably different charges on the ions. And the mechanism can be that it's come from the two different plasma, the triggering and the main one, or probably a movement, because Igal talked a bit about the spot, the lifetime of the spot. Here at multiple, at few kiloamperes, there are multiple spots. So probably that can come from the movement of the different spots, creating different ion groups. And with this time of flight measurement, we are able to see that even though the data is quite scattered, the most probable velocity is around 40 kilometers per second. The results of our 50 pulses shows that the velocity of the first peak, the mean velocity of the first peak is 43 kilometers per second with a standard deviation of 12 kilometers per second. And those velocities are higher than the one found in the literature because there is still few literature on such high current vacuum arcs. For the second peak, it's slower in average. We have a second mean velocity of 36 kilometers per second. And this behavior can be seen when we move the overall experimental setup along the axis. We can see that the first peak is always faster than the second one, which is always faster than the third one. So yeah, for on this range of distance, so from 12.5 centimeters to 30.5 centimeters. There is no significant evolution of the velocities. So probably it appears before, but these are preliminary results, so we'll have to investigate a bit more about that later. So to conclude, we've been able to find that there is two different plasma, the ignition one with a higher electron temperature but a lower density, and the, let's say, operation arc, which is longer with a longer density, with a higher density, but a lower electron temperature. We have been able also to observe different ion groups whose origin remain quite unknown at the moment. There is still few works on high current vacuum arc, as I already told. And so the perspective, we plan to investigate on the influence of the cathode material. So for example, we plan to use titanium to compare a bit. Ion charge state measurements with the help of the Laplace laboratory of the CNRS, and investigation of the dominant force with the Laplace 2 and PlasmaSolve, which is a startup in simulation as the PJP project. Because at the moment we do not know if the dominant force that ejects the plasma is more about the pressure or the electrostatic forces, and we should investigate too on the ion creation mechanism. We were really thinking about that. So thank you very much for your attention, and this work has been done in the frame of an 2020 program, PGP project, which was supported by the European Union. Thank you very much.
Thank you, Etienne, for your paper. Thanks a lot for being on time. You were a bit fast, so that's great because we were a bit late. So we have again time for questions from the audience. So are there any questions? So I have one. So no, maybe not only for you, Etienne, but also for people working in that field, like Roman, Antoine, Igual. So we have seen with your talk, Etienne, and the two previous talk that you can have a low current or high current strategy, so vacuum arc thruster, and it's really different because others were in the amps range. You are in the kilo amps range.
Yes, exactly.
So do you think that in short, the physics is the same and ion creation and acceleration mechanisms are the same? You just give more power in the case of high current thruster. So this is the first question. And the second one is super tricky. Is one approach story better than the other one? So low versus high current. And I don't have the answer myself. So it's also a question for the audience, but not only for you. But for the first one, about the physics behind, do you think it's the same?
No, it's not really the same as I read. For the high current, you have really interesting phenomenon occurring even on the anode. And I think that the people working in have shown in the simulation that the ion creation is quite different with the really high current. So correct me if I'm wrong, but yeah, the physics is quite different. You don't have the same properties in vacuum arcs.
I can also, Stefan, if I may.
Sure.
Yeah, so it seems to be very different because usually electron temperature in low power arcs are around 2 eV.
Mm-hmm.
Yeah, so it's really different, and also you have additional magnetic fields and so forth, and you have additional acceleration by that. So yeah, it's quite different. That's at least my opinion.
And about the comparison between the two technologies?
you don't really consider that we answer here, right?
I was hoping an answer.
Well, I think I can, from my unbiased opinion, is that for CubeSats, really, I aim this technology for the lowest of CubeSat, the smallest CubeSat, the low. I mean, we basically can operate a 1 watt device, really, a whole system, 1 watt, and that's it. So from this respect, it's difficult to compete with. When you go to these higher powers, it's maybe Etienne can answer.
Can you repeat your question, please? Again?
I said that on the as we saw it in our development, we aimed it to the smallest of CubeSats. Okay, the lowest power to the smallest devices you can imagine, because we can make it really, really small, really, like I said, 1 watt thruster, EP thruster, 1 watt. I mean, it's amazing. And the whole system can be the size of a few millimeters in principle. Okay, so it's really, really small. So this is our intention in the ability to scale down. But you go to now higher power. It's not high power, but higher power and much more energetic pulses and shorter and so on. So maybe it's interesting to compare this to then thrusters in your same power scale. Yeah, or let's say
it can be interesting.
Yeah. Or can you reduce your system's power to the levels I showed? Let's say, for example.
Yes, I don't have the answer on your question because I'm not in charge of the development of this thruster. This is the COMAT, which is in charge of the development of this thruster. So I'm working more on the experiment on the plasma jet to give experimental data to the simulation teams and to investigate the unknowns of this plasma jet.
I mean, from what I understood from COMAT, it seems that with a higher current, you can achieve a higher velocity for the ions. Maybe due because you produce a more multiply charged ions. But it's still an open question, I would say. But that was my feeling from what they say. That was my understanding, I would say.
Okay, it will be time to stop and move to the next speaker, but I think we can also discuss that this afternoon because the first invited lecture this afternoon is by COMAT on their, between brackets, high power vacuum thruster. So this may be an interesting point to be discussed this afternoon. Thanks a lot, Etienne, for your interesting talk.
Thank you very much.